In this lesson, we're going to look at the expected values of continuous random variables. So let x be a continuous random variable, and let f of x be the PDF of x. Then the expected value of x is e of x is the integral from negative infinity to infinity of x times f of x dx. If you've already done the lessons on discrete random variables, this should look somewhat familiar to you. So for discrete random variables, just as a reminder, if a discrete random variable x has PMF, p of x, then the expected value of x is just the sum over all points on which x has positive probability of x times p of x. And if we replace the sum by an integral and p of x by f of x dx, we have, we would end up replacing it with the formula for a continuous random variable. Notice that since f of x is defined over the whole real numbers and it's just 0 in most places, this integral makes sense. So we can just integrate from negative infinity to infinity and not worry about restricting only to the points on where x is positive in the definition. So let's look at an example. If x is a continuous random variable with PDF f of x equals 3/7 x squared for 1 less than x less than 2 and 0 otherwise, then the expected value of x is, by definition, the integral from negative infinity to infinity of x times f of x dx, which is equal to the integral from 1 to 2 of x times 3/7 x squared dx. And that's the integral from 1 to 2 of 3/7 x cubed dx. Then you can use the power rule. So this is x to the 4 over 4, and that makes the fraction 3 over 28. And we evaluate x from 1 to 2. So we get 48 over 28 minus 3 over 28, which is 45 over 28. We can throw out the rest of the real line because the integral from negative infinity to 1 of x f of x dx is the integral from negative infinity to 1 of 0 dx, because f of x is 0 outside of the interval from 1 to 2. And similarly, the integral from 2 to infinity of x times f of x is the integral from 2 to infinity of just 0 dx, which is just 0. So whenever we actually evaluate the expected values, we only need to be concerned with the intervals on which the PDF is non-zero. If f of x is a continuous random variable that is bigger than or equal to 0 everywhere, and f of x is the CDF of x, then we can write down an alternate definition of the expected value. The expected value is the integral from 0 to infinity of 1 minus capital F of x dx. And to prove this, we just use definitions here. So the integral from 0 to infinity of 1 minus f of x is the integral from 0 to infinity of the probability that x is bigger than or equal to x. So remember that f of x is the probability that x, the random variable, is less than or equal to little x. So 1 minus that is the probability that x is bigger than x, or because it's continuous, you could write bigger than or equal to x. And this probability, by definition of a PDF, is the integral from x to infinity of f of t dt. So we can just integrate f of t over that interval, which is from x to infinity. To go to the next line, we can swap the order of the integrals. So instead of integrating dt dx, we can integrate dx dt and go from 0 to infinity and then from 0 to t. Now, there's no x in this inner integral, so integrating from 0 to t, f of t dx, just leaves us with t f of t. So we have the integral from 0 to infinity of t f of t dt, which if you wanted to rewrite this in the more familiar way, you could write this as x f of x dx, and it's the integral from 0 to infinity. But we've assumed that x is always bigger than or equal to 0, so f of x is 0 from negative infinity to 0, and therefore that gives us just the expected value of x. Just like with discrete random variables, you can pull out constants. So the expected value of a constant times x is the constant times the expected value of x. And to show this, you just use the integral. So integrate the expected value of cx is the integral from negative infinity to infinity of cx f of x dx. Because whenever x equals little x, then cx is going to equal c times little x. And the c can be pulled out of the integral, which leaves us with this integral, the integral from negative infinity to infinity, x f of x dx, which is e of x. So e of c times x equals c times e of x. Also, given two continuous random variables, x and y, the expected value of x plus y equals the expected value of x plus the expected value of y. So that held for discrete random variables. It also holds for continuous random variables. And to show this, the expected value of x plus y, we use the joint PDF. So this would be the integral from negative infinity to infinity of the integral from negative infinity to infinity of the value of x plus y, f of x, y, dx dy, where f of x, y is the joint distribution. And distributing, we get x f of x, y and y f of x, y dx dy. And for this first integral, I'm going to swap the order of integration. So instead of doing dx dy, we will do dy dx, and we'll pull the x outside, since this is an integral with respect to y. For the second integral, we don't have to swap. So we have dx dy, we'll leave it dx dy, but we can pull this y outside of the inner integral, since this integral is with respect to x. And the integral from negative infinity to infinity of f of x, y dy, that integrates out the y, and that leaves us with the PDF of x. And this integral from negative infinity to infinity of f of x, y dx integrates out the x and leaves us with the PDF of y. So we get the integral from negative infinity to infinity of x times f of x dx plus the integral from negative infinity to infinity of y times f of y dy, which this is e of x and this is e of y. So we get e of x plus e of y. And in particular, if we want to sum all this up, if x and y are random variables and a, b, and c are constants, then the expected value of ax plus by plus c is a times e of x plus b times e of y plus c. So expected value is linear on both discrete and continuous random variables, which is nice. It's fewer things to remember. It's always linear. It doesn't matter whether the random variables are discrete or continuous. Another effect that you'll be familiar with if you've done the lessons on discrete random variables is that if x and y are independent and continuous random variables, then the expected value of xy is e of x times e of y. So you can break out products over expected values if the random variables are independent. So that is the condition that we need. So for continuous random variables, they're independent if the PDF, the joint PDF f of xy, can be written as the product of the PDS, f of x times f of y, over a rectangular region R. So I'm going to let R be what I've written as closed intervals from a, b, cross CD, without trying to go into too many details about whether the endpoint should be open or closed. But these endpoints could also be negative infinity and positive infinity, in which case they should be open intervals usually. So the expected value of xy is the integral from negative infinity to infinity of dx dy of, so the value would be x times y, f of xy. And here we can split up the integrals using independence. So the inner integral is over dx, so we'll pull out the x and the f of x into one integral x f of x dx, and the integral over y is y f of y dy, so we can pull that out into a separate integral. And the integral of x f of x dx gives us e of x, and the integral of y f of y dy gives us e of y. And so, in general, something that I've been using above is that if g of x is a function, and we compose g with a random variable capital X, then the expected value is, oops, this should be a capital X here, g of x times f of x dx, the integral from negative infinity to infinity of that. And that's because the random variable g of x is going to take the value g of little x, whenever the random variable capital X equals little x. So if we do an example of that, we could let x be a random variable with PDF f of x equals 1 over x from 1 less than x less than e. And we can find the expected value of x cubed plus 1. So by linearity, the expected value of x cubed plus 1 is e of x cubed plus 1. So we really just need to find e of x cubed and then add 1 to it. Now using the formula for expected value, we have an x cubed in here, so we're going to use that g of x is x cubed times the PDF, and the PDF in this case is 1 over x from 1 to e. So that's how we get the 1 over x is the, that's little f of x, and then it's only going from 1 to e, it's 0 everywhere else. So this is x squared, oops, excuse my silly mistake here, x squared dx. And then by the power rule, this is x cubed over 3 evaluated from 1 to e, or e cubed minus 1 over 3. So the expected value of x cubed plus 1 is e cubed minus 1 over 3 plus 1. Don't forget to add that constant back in, and that gives us e cubed plus 2 over 3.